Today your assignment consists primarily of trying to convert from standard form to the vertex form of a quadratic equation by using the completing the square method. So let's go back a little bit and talk about some of the things we already know about how to do this. First, when faced with a problem such as this is already in vertex form. We can already see that it's going to have an x-coordinate of -8 and a y-coordinate of 6. Very easy to find the vertex. This is a great form. But do you remember how we could go back to standard form from this? Well, if you're remembering what we did in the past, we would FOIL out the first part of this. This would FOIL out, and we'd get x squared plus 16x plus 64. But we can't forget that we still have this. So I need to add the 6 to the end. By combining like terms, I'd end up with y equals x squared plus 16x plus 70. And that would be the standard form of this quadratic equation. But the question is, how do I start with this and get back to this easily? Well, the answer lies in completing the square. So let's review that for a second. Right here, I have a polynomial that I would like to make a perfect square trinomial. I remember that in order to make this a perfect square trinomial, I start looking at this term, and I ask myself, what is 1/2 of that middle number? That would be 3. From there, I asked myself, what happens when I square that? And that would give me the 9. And so I remember that I can create a perfect square trinomial fairly quickly and fairly easily. Now we're going to apply that to changing from standard form to the vertex form of a quadratic equation. Here is that same idea, but now I have the equation of a parabola. I would like to figure out where the vertex of this parabola is by converting this into the vertex form. As I had in the last problem, I can see that I almost have a perfect square trinomial. I'm just missing a third term. Now, the problem is I can't just go willy-nilly and add that third term because it's an equation. And if I add anything to this side of the equation, I would have had to add it to this side. So the solution lies not in adding a single value to it, but rather to adding 0. Here's what I mean. I can't just add 9, but I could add 9 and subtract 9 at the same time. Combined, I've really only added 0. And that's what I want. I have not changed the value of this. So looking at it, I can now look at just the first 3 terms, here to here. And that is the perfect square trinomial that I was looking for. Now I can simply rewrite this as x plus 3 quantity squared, and then I still have this minus 9 at the end. And like magic, it is now in vertex form. I can tell that the vertex is going to have an x value of -3, easy to spot because right here, and I could tell that it's going to have a y value of -9. Again, easy to spot because of the k value right here. So let's look at this process a little more closely with a little more complex of a problem. First, I can see that I have a quadratic equation, and I can see that it's almost a perfect square trinomial. I need to figure out what value I want to have being added that would make this a perfect square trinomial. So I think to myself, half of 12 is 6, and 6 squared is 36. 36 is what I want, but what I really have is 20. So now I have to ask myself, what do I need to add to 20 to get what I want, which is 36? Well, that answer is pretty obvious. I need to add 16. So I'm going to go ahead and do that. I'll have y equals x squared plus 12x plus 20. And now I can't change the value of this, so I want to add 16, but I will also subtract 16. That way I've actually only added 0. So now I can go ahead and combine like terms that I want to combine. Y is equal to x squared plus 12x plus the 36 I was looking for, and I'll still have this minus 16 out here. Grouping it like this, I'll be able to factor it as x plus 6 quantity squared minus 16. And I've pretty much solved this problem. It is now in vertex form, and I can see that the vertex is going to be at negative 6, negative 16. Easy to graph from there. Let's try another one. In this case, I can see that it's almost a perfect square trinomial. I have x squared and a negative 4x. I just want a different number here than I currently have. So I have to ask myself, what number do I want there? Half of negative 4 is 2, and negative 2 squared is positive 4. I don't currently have positive 4. I have negative 3. So I have to ask myself, what do I need to do to the negative 3 in order to make it a 4? And in my world, I have to add 7 to both. I have to add 7 and subtract 7 so I don't actually increase the value. So y is going to equal x squared minus 4x minus 3. Here's the plus 7 I need and the minus 7 I need. Notice that I did not change the value. It's still worth exactly the same amount. But now I can put this stuff together here. I'll end up with y x squared minus 4x plus 4 minus 7 on the outside, which means it can factor as x minus 2 quantity squared minus 7. The vertex is going to be at 2, negative 7. Easy to graph. Try this one on your own. Figure out what value you need to change this 7 to in order to make this a perfect square trinomial. Then go ahead and add what you need and subtract the same amount so you don't change the value. Factor it and figure out where the vertex will be. I'll give you a few seconds to do that. Why don't you pause this video, try it, and we'll see how you did. By now, you should have figured out that what we need is y is equal to x squared minus 6x plus 7, and since half of 6 is 3 and 3 squared is 9, I'm going to add 2 to make 9 and subtract 2, so I'm not changing the value of the trinomial. Then I'll have y is equal to x squared minus 6x plus 9 minus 2. Looking at the trinomial here, I can say this is y is equal to x minus 3 quantity squared minus 2, and the vertex is going to be at positive 3, negative 2. Easy to graph. Sometimes math teachers are just cruel and unusual. Sometimes we're just unusual, but in this case, we're both. As I look at the problem here, it looks like a very normal problem, but I'm noticing out here there's a negative in front of the y. I know for the vertex form to work, this has to be a positive. But I also know that if I put the negative to this side by multiplying both sides by negative 1, I won't have a perfect square here. And I need a perfect square here to get a perfect square trinomial. What is a math student to do? Well, a math student is really to ignore the negative until the very end. So I will approach this problem like I've approached all of them so far. I'm going to figure out what half of 2 is, which is 1. Squared, that'll be 1. And that's what I want to see here. I wish this negative 3 was a 1. So I realize I need to add 4 to make this negative 3 a 1. So I'll both add 4 and subtract 4 so that I don't change the value. We'll have negative y, x squared, plus 2x, minus 3. Now the new stuff we're doing, plus 4 and minus 4. This will give me negative y, x squared, plus 2x, plus 1, minus 4. Grouping this trinomial, I'll have negative y, x plus 1, quantity squared, minus 4. I'm not done yet. In order to finish this problem up, I am going to have to take care of that negative that we talked about before. This can't be negative. So I'm going to choose to take negative 1 and multiply both sides of the equation by negative 1. When I distribute the negative, I'll end up with positive y on this side, negative 1 times x plus 1 quantity squared on this side, plus 4. Again, I can find the vertex very quickly at negative 1, positive 4, but I recognize that because of the negative out front here, this parabola would open downward if I were to try to graph it. Let's look at how that works again. Here's another problem. I'm going to go ahead and complete the square. I recognize that I need half of 4, which is 2, squared, which is positive 4, instead of this negative 3. So I need to add 7 to both sides. I am completely ignoring this negative for right now. So here's my negative y, x squared, plus 4x, minus 3. That was the original. I wanted it to be a 4, so I'm going to add 7 and subtract 7 at the same time, so I haven't changed the value. Now I can rewrite this as negative y, x squared plus 4x plus 4 minus 7. Grouping these, I get negative y, x plus 2 quantity squared minus 7. And now I can deal with that negative that's on the outside of the y. It's time to get rid of this. So I will say negative 1 times negative y and negative 1 times x plus 2 quantity squared minus 7. When I distribute the negative, I end up with positive y, negative 1 times x plus 2 quantity squared plus 7. I can see that my vertex is going to be at negative 2, 7, and because of the negative out here, my parabola opens downward. One last twist, just to really make you all frustrated. In this case, I'm looking here, and I've got a negative x squared. That's not right. How can we possibly do this problem? Well, we're going to get rid of the negative on this side the same way we got rid of a negative on this side. And that involves multiplying both sides by negative 1. So I'm going to take negative 1 times y on this side, and negative 1 times negative x squared minus 6x plus 4 on this side. Using the distributive property, I'll get negative y equals positive x squared, positive 6x, and negative 4. From here, it's very easy to do this problem. I'll do it like I did before. I can see that half of 6 is 3, 3 squared is 9. This isn't a 9. I need to add 13 to both sides. So I'll have negative y, x squared plus 6x minus 4. I'll add 13 and subtract 13 at the same time so it doesn't change the value of it. I'm left with negative y, x squared plus 6x plus 9 minus 13. Now I can regroup my trinomial and factor it. Negative y, x plus 3 quantity squared minus 13. And my last thing is to go ahead and deal with this negative again. I just moved it over for one little time. So negative 1 times negative y, negative 1 times x plus 3 quantity squared minus 13. And I should end up with y equals negative 1 x plus 3 quantity squared plus 13. Basically, our job is to handle this problem twice. Deal with the negative once at the very beginning, deal with the negative once at the very end. Other than that, it's the same old stuff.